Okay, hello everybody. Give me great pleasure this afternoon to introduce our speaker. Our speaker is David Levinson. He's from Lockheed Martin, and he did his undergraduate at Cornell, a graduate at University of Texas, as well as at Stanford. And he's been with Lockheed Martin for over 30 years now. He's had a distinguished career as a dynamicist over there, including winning several awards. He won the President's Award at Lockheed. He's a fellow of the American Society of Mechanical Engineers, a fellow of American Astronautical Society, and so on. So I don't want to eat up his time, so just help me welcome David Levinson.
Get the lights in there. There we go. This is something that many of us older people remember very well. It was the launch of Sputnik 1 on October 4th, 1957. Now, this is going to be a technical talk, but since most of you weren't around when all of this happened, I'm going to, before I get into the technical material, I'm going to give you some historical background to put it in perspective. First of all, you might be wondering how it was that the Soviet Union beat the United States in putting the first satellite into orbit. And it's a complicated story, and it goes like this. On May 20th, 1955, the United States National Security Council approved a program to put a scientific satellite into orbit as part of the International Geophysical Year. Now, this year was really an 18-month period that ran from July 1st, 1957 until the end of 1958. The goal was to launch the satellite by 1958. The details of how to accomplish this were left to Donald Quarles, who was President Eisenhower's Assistant Secretary of Defense for Research and Development. Quarles appointed a panel called the Ad Hoc Group on Special Capabilities, which was assigned the task of selecting a satellite program. The panel was chaired by Homer Joe Stewart of the Jet Propulsion Laboratory and included representatives from the Army, Navy, and Air Force. During the Stewart Committee's meetings in July of 1955, 3 options were considered on how to launch the satellite. Option number 1 was the Army proposed an upgraded version of the Redstone rocket. Option number 2, the Navy proposed using a small satellite and a new 3-stage launch vehicle based on the Naval Research Laboratory's Viking sounding rocket. And option 3, the Air Force proposed a much larger satellite launched by the as yet untested Atlas intercontinental ballistic missile. The Stewart Committee issued its report on August 4th, 1955, and voting 5-2 for the Navy proposal. As you might imagine, this startled and infuriated the Army team, but it even surprised the head of the Navy team, who said, "I thought they'd win too. They had a rocket and we didn't." The Army team didn't take this lying down. They protested that they had a proven rocket, the Redstone, and could orbit a satellite much earlier, by January of 1957 instead of sometime in 1958. So under pressure, the Stewart Committee re-voted. But again, the vote came out 5-2 in favor of the Navy proposal. And so on September 9th, 1955, the Naval Research Laboratory was authorized to proceed with their option, which was given the name Vanguard. Project Vanguard received tremendous publicity throughout the second half of 1955 and all of 1956. In fact, there was so much publicity that the chief of the project got nervous and warned that there might be only 1 success in 6 attempts. 1 out of 6. The actual result turned out to be better than that. 3 successes in 11 attempts. What's more, although Vanguard was a Navy project and the Navy was part of our military, the Navy kept stressing the non-missile nature of the product referring to the rocket as a vehicle. This resulted in a large volume of mail from people asking who was going to be riding in it. Eisenhower himself announced that the Vanguard program would launch a satellite by means of an entirely peaceful rocket that could not be used as a missile. Even the French made fun of this. One French editorial said, and I quote, "Not only are we going to get an American satellite, but a virtuous American satellite, probably as virtuous as prohibition," end of quote. Meanwhile, on September 20th, 1956, the Army under Wernher von Braun successfully launched a Jupiter-C missile, which made a flight of more than 3,000 miles, a new distance record for a Cape Canaveral launch. This caused a strict order to be issued from Washington to keep the successful flight a secret from the public. But several magazines, including Life, found out about it and published the facts. One fact they did not know was that Eisenhower had ordered that there be no accidental satellites. John B. Medeiros, General Medeiros, was the commanding officer of the Army Ballistic Missile Agency, and in his memoir, Countdown for Decision, he wrote, and I quote, "For this test shot, we were using a dummy fourth stage. If we had put a solid propellant into the fourth stage, instead of the inert material we were using to get it to the right weight, we could have fired that particular missile into orbit as a satellite. We didn't do this for the simple reason that we were forbidden to do so. We had no mission for putting up a satellite. Vanguard had that assignment, and nobody had any intention of giving us that mission. So we put sand aboard the fourth stage instead of powder," end of quote. Furthermore, Medeiros was compelled to issue a directive to stop the Jupiter-C test program at once. However, he took the liberty of ordering all Jupiter-C hardware to be put into protected storage so that it would suffer no deterioration. This latter decision would prove fortuitous. While all of this was going on, Eisenhower was trying to establish an international principle of freedom of overflight, which was the right to send reconnaissance and other satellites over another country for any non-lethal purpose without permission. On July 21st, 1955, at a U.S.-Soviet summit in Geneva, Switzerland, Eisenhower proposed this freedom of space policy. The Soviets rejected it, saying that it was an obvious American attempt to accumulate target information. On October 4th, 1957, news of Sputnik reached the Redstone Arsenal in Huntsville, Alabama, where von Braun and General Medeiros were attending a dinner for Wilbur Brucker, who was the Secretary of the Army, and Neil McElroy, the incoming Secretary of Defense. Von Braun literally begged Secretary McElroy for permission to implement a satellite project. Medeiros recalls von Braun saying, "For God's sake, turn us loose and let us do something. We can put up a satellite in 60 days, Mr. McElroy." In retrospect, it turns out that Eisenhower was wiser than people gave him credit for at the time. For by allowing the Soviets to launch their first satellite and not complaining about its overflight of the United States, Eisenhower was able to establish the freedom of overflight principle on his own without the need for Soviet concurrence. The principle turned out to have a stabilizing influence on the Cold War. The ability to see what the other side was doing helped to ensure that leaders on both sides did not make decisions based on faulty intelligence. Both the Americans and the Soviets benefited from the capability, and the world was safer as a result. What's more, allowing the Soviets to launch the first satellite made NASA and Apollo possible. If the United States had put up the first Earth satellite, it is highly unlikely that NASA ever would have been created or that Americans would have walked on the moon in 1969. However, the Soviets didn't hesitate to exploit the propaganda opportunity that Sputnik provided. TASS, the official Soviet news agency, said, and I quote, "The tremendous launching of the first man-made satellite makes a tremendous contribution to the treasure house of world science and culture. Artificial Earth satellites will pave the way for space travel, and it seems that the present generation will witness how the freed and conscious labor of the people of the new socialist society turns even the most daring of man's dreams into reality." Now, some of the American press joined in the pro-Soviet propaganda. For example, a Dallas Morning News editorial said, "Russia's achievement is something to think about. In that totalitarian country, scientists are told what to do. They can be quickly mobilized and their mass effort directed at any single objective. This is not advocating anything of the sort here, but fully recognizing some advantages of tight totalitarian control will be helpful to our democratic processes. Right, there's nothing like a little totalitarianism to further the democratic process. You can see that nothing has changed about the press. Now, on November 3rd, 1957, the Soviets further rubbed our noses in it by launching Sputnik 2, carrying a dog named Laika, who died in space. Of course, animal rights advocates around the world were outraged, and so nothing has changed on that score either. In any event, it was time for an American reply. And on December 6, 1957, Vanguard TV-3 rose 4 feet into the air before falling back on the launch pad and exploding. This was America's answer to the Sputniks. It was carrying a 3-pound satellite compared to the 184-pound Sputnik 1 and 1,120-pound Sputnik 2. Now, the reason for the vast discrepancy in weight was that Soviet nuclear warheads were significantly heavier than their more advanced American counterparts. So the Soviets needed to build more powerful boosters than the Americans to deliver the warheads. A few days after the Vanguard failure, the Soviet delegate to the United Nations asked whether the United States was interested in receiving aid earmarked for underdeveloped countries. Not surprisingly, von Braun soon was given explicit orders to launch his satellite as quickly as possible. Medeiros agreed with William Pickering of the Jet Propulsion Laboratory that JPL, rather than von Braun's team, should do the satellite work. Now here's the successful launch of Explorer I. On January 31st, 1958, Explorer I was successfully launched atop a Jupiter C rocket. Now, von Braun's associate, Ernst Stuhlinger, had the most critical job that night. Telemetry was fed to him so that he could determine the instant to fire the second stage. The first stage burned out 157 seconds into the flight at an angle of 40 degrees to the horizontal. Explosive bolts and springs separated the first stage from the upper portion of the vehicle, and small attitude control jets rotated the upper portion into a horizontal orientation. Stuhlinger calculated when the vehicle had reached this orientation, which was 250 seconds after first stage burnout, and he sent the command manually to fire the second stage solid rocket motors. And for this, Stuhlinger became known as the man with the golden finger. Now, the third and fourth stages were fired automatically by onboard timers. In the blockhouse, Al Hibbs of the Jet Propulsion Laboratory was making rough trajectory calculations based on tracking data as well as Doppler measurements of radio signals sent back from Explorer I. Half an hour after launch, Hibbs told an anxious General Medeiros that he could conclude with 95% confidence that there was a 60% probability that the satellite was in orbit. And General Medeiros blew his stack. He said, "Don't give me that crap, Hibbs. Is it up?" And Hibbs replied, "It's up." All right, now here's what it looks like. This is the satellite. It's a little bit taller than I am. I'm 6'6", and this is almost 6'9", but only weighed a little under 31 pounds. It was mounted on a drum on top of the booster. Here's the Jupiter C, and it was mounted on this drum, which was spun up on the launch pad. So here's that 6'8" satellite you saw, and this drum was spun, and it looked like this on the launch pad. Prior to launch, they spun the drum up at 550 RPM. At 70 seconds after liftoff, they increased the rotation rate to 650 RPM, and at 115 seconds after launch, up to 750 RPM. So here's what it looks like. It came off the booster horizontally, and a little bit later, it was doing that. Now, this was regarded as an anomaly. Now, in order to ask why was it regarded as an anomaly, you have to know what an anomaly is. Something inconsistent with what would actually be expected. So the question is, why would something else be expected? Well, we'll get into that. But this is what was going on in the engineering world, and I will come back to this in a minute. What was going on in the scientific world is something else. A Geiger tube on board the satellite was sending back data, and here are the data that the satellite sent back. Now, if you notice, these empty circles here are 30 radiation counts per second. The black ones are 0 during a 2-minute period. Now, 30 counts per second is 3,600 counts in 2 minutes. So here we have 30 counts there were approximately 30 counts per second, and here, which was 3,600. So think of this as 3,600 counts in 2 minutes, and these 0 counts in 2 minutes. So what was going on here? We found a spot in space where there's absolutely no radiation at all. Now, that was impossible. There's radiation everywhere in space. Well, what they discovered later, after looking at the data, was that we believe that the extremely low output rate is caused by very intense radiation, which jams the Geiger tube so that it puts out pulses of such low height that they are below the threshold of the counting circuits. And laboratory tests show that this first happens for the present equipment when the radiation reaches an intensity that the counter would produce 35,000 counts per second. So in the laboratory, they showed that not only were there no counts here, but there was 10 times as much radiation as here. And so this is the discovery of the Van Allen radiation belt. So the historical fact is that the equipment read that there was no radiation whatsoever, and that's what gave them the data that let them realize that this was actually a radiation belt, not a radiation hole. Now, so here's a picture of the mission was declared a success because it succeeded two things. It succeeded in making it into orbit, and it discovered the Van Allen radiation belt. So scientifically, it was a complete success. Now, this is William Pickering, who is head of the Jet Propulsion Laboratory. And here's James Van Allen, who is a physics professor at the University of Iowa, who designed the radiation detector, and after whom the Van Allen belts are named. And this is Werner von Braun, who is Werner von Braun. Now, but back in the engineering world, that's the science world. Let's get back to the engineering world. We still don't know what caused this anomaly. There's this big question. Now, to answer this question, we need to go back 200 years to Leonard Euler, who is the father of rigid body dynamics. And some of you have heard the name Euler, but I'm going to give you some background on Euler. Leonard Euler is considered to be one of the 4 greatest mathematicians in history, the other 3 being Archimedes, Newton, and Gauss. Euler lived to be 76 years old and created enough mathematics to fill 74 large volumes consisting of 866 items, including papers, books, elementary textbooks, books for the non-scientist, and technical manuals. And this does not include the projected 15 volumes of correspondence and notebooks that are still being compiled after more than 200 years. Euler published more pages of mathematics than any other mathematician, and he possessed a trait that is rare among most mathematicians. He wrote clearly so that his work was understandable, and which added greatly to his fame because all of that stuff he published was people could absorb. And Euler made contributions to calculus, analysis, number theory, complex analysis, calculus of variations, differential equations, probability theory, topology, optics, electricity and magnetism, hydrodynamics, astronomy, and mechanics. And we aerospace engineers use many things named after Euler almost every day, such as Euler angles, Euler's theorem on rotations, Euler parameters, sometimes called a quaternion, Euler's kinematical equations and Euler's dynamical equations. So after going back through all the published literature on dynamics, engineers were faced with a revelation. And this is the revelation that in 200 years of papers, there was nothing that could explain what was going on with this satellite. Now, I'm going to do a technical digression here because I'm going to be showing a lot of animations, and I want to make a distinction here between an animation and a cartoon. Now, the animations we're talking about are the animating solutions of the initial value problem in dynamics. Now, what's that? Well, the problem has an input and an output. The input is a complete description of the geometric and inertia properties of the system, a complete description of certain forces acting on the system, and a complete description of the motion at time t equals 0. Then you formulate and solve differential equations of motion. And the output is a description of the motion of the system for t greater than 0. Now, this isn't the same thing as a cartoon. Here, we're able to animate both input and output. We have input, we have output. We animate them both. But in a cartoon, it's different. We input a complete description of the geometric properties of the system, but we also input a complete description of the motion of the system for t greater than or equal to 0. We input the whole motion. There's nothing to calculate. And this is true even if the motion violates the laws of physics. I'm sure all of you have seen cartoons where there's a cartoon character runs off the cliff and does not fall until he realizes that he's not standing on anything, and then out of thin air he pulls out an oops sign, and only then does he fall. Okay, well, you can do things like that with cartoons, and that's not what we're doing here. Now, there's some interesting epistemological and metaphysical things one can gain from looking at cartoons, but that's a subject of a different talk. There's no output at all in a cartoon. The whole cartoon is input. And we animate the input because that's the only thing there is. Okay, and that's not what we're doing. Okay, so we're not going to be doing cartoons. So you can see the difference. Now, the first thing I want to show you is a Carpenter Square. Many of you have seen this. You can see one in any hardware store. And I'll put some dots on it. If you draw lines down the middle of these two legs, there's a red dot here, a green dot here, and a blue dot here. And this is all taking place in a vertical plane where this resides. And what I want to do is I want to launch this in the plane at an angle of 20 degrees to the horizontal, make this point start off at 20 feet per second, and give it an angular speed of 20 radians per second. Now, you might think, well, there must be something special about the number 20. Actually, there isn't. It just turns out that I was trying to find numbers that would keep this thing on the screen when I animated it, and that's what they were. So we're going to do that. And if you launch it, this is what it looks like. The red dot follows this trajectory, and the green dot follows that, and the blue follows that. So that's what that looks like. Now I'm going to add another dot to the a fuchsia dot. There's the fuchsia dot. And this dot is rigidly attached to this. It doesn't touch it, but think of some invisible piece of plastic that holds it there. And now we're going to launch this again. And I'm going to do this animation. So I will find the escape button. And now let's see if I can do this. Is it the minimize? Oh, good. Okay, let me. All right, now we're going to launch this thing, and it's going to fly through the air. We're looking at solution of differential equations of motion, mind you. This is output. Okay, so now you've seen that. So it looks like that. It has a different trajectory. Now, I'm sure all of you are aware that this is the mass center of the system. But I want to say something about mass centers that you probably never heard anyone say before. And contrary to common usage, it isn't correct to say that the mass center moves through space while the body rotates around it, any more than it is correct to say that the green dot moves through space and the body rotates around it. There's nothing different about this trajectory except that in some sense it's simpler than the others. It makes a simpler trajectory. But every one of these points is moving through space on some trajectory and the body is rotating. So to say that the mass center moves through space and the body rotates around it is simply not good mechanics. Now, I want to show you a few more of these. But I want to leave you with the conclusion that mass distribution matters. Now, we're going to let me find my escape button. Yeah, it's dark. Yeah, let me just enough to see the. It's so dark in here, I can't find my button. Just that's good. Okay, there we go. Now, I'm going to pull up the animation. And this is it. All right. Now, what you're looking at is a rectangular plate right here with some X's on it so you can find the center. And it's clamped between two halves of this green rod along the edge here. And the whole thing is on a revolute joint here that is horizontal. So the plate can rotate, it's free to rotate. But it's resisted by a torsional spring that exactly balances the moment caused by the weight acting down through the center of mass. So it sticks straight up in the air. Now there's a motor down here that will cause this to rotate about the vertical. So if I turn on the motor, what do you think will happen? This will start to spin, and what will the plate do? The plate should rotate out because you get a centrifugal force acting through the mass center. So we'll see what it does. Start it up. Again, you're looking at differential equations being solved. And I have a little red line in space that I just put there so you can see that there is a cone angle. So we'll let it spin around and then come to a stop. So as it slows down, you should see it straighten up again as the spring takes over and pulls it back. All right, now I'm going to show you another one similar to this. Now, if you're wondering why I'm restarting this all the time, it sometimes hangs up if I don't. Sorry. All right, now, this time I've clamped it along one of the diagonals so that the mass center is on the vertical axis. When I start this rotating, what do you think will happen? Any guesses? All right, let's see. So even though there's no centrifugal force initially on the mass center, something's going on that makes this thing want to rotate out, about the horizontal revolute joint. So there's something complicated going on here, right? We'll let that one slow down and stop. Then I'll show you another one. All right. Now I've got it clamped along some arbitrary line on the plate. So the mass center is sticking out and everything looks kind of arbitrary. Now if I spin this, what do you think will happen? Well, let's have a look. Plate doesn't rotate. So something very interesting is going on, right? It turns out that this is not some arbitrary line. What is it? Anybody know what that? It's a principal axis. For what point? It's not for the mass center. The principal axes for the mass center are parallel to the edges of the plate and perpendicular to the plate. This is a principal axis of inertia for the corner. So the fact is that a lot of the things some people think that the only points that have principal axes are mass centers, but there's two things here. Every point in the body and also every point in space has a set of principal axes for this plate, and they have physical significance. This really does mean something. Now I'm going to show you another animation. All right, now here's two identical barbells. The plates and the bars weigh the same. And the only difference is the plates are closer together here than they are there. And I have them hinged here on horizontal axes, and they're leaning, both barbells are leaning 1 degree past the vertical toward the mat. Now I'm going to release it from rest, and the question is, what's going to happen? Now, one thing I might say is that if I drop these both off the Leaning Tower of Pisa, they'd hit the ground at the same time. Now, there's only three possibilities. Either they hit the mat at the same time, the one with the plates far apart hits first, or the one with the plates close together hits first. Now, what's it going to be? Together. All right? Let's see what happens. Okay, so there was a big difference. Okay. So the conclusion from these was that mass distribution matters, and the conclusion from this was mass distribution matters. That's the end of my digression. Now we're going to get back to Euler. Now, here is Euler's paper where he first published his very familiar equations. And the title, this is in French, is published in 1765. And this title is Rotational Motion of Solid Bodies Around a Variable Axis. And this goes from pages 154 to 193, and in the middle there are these equations. Now I claim these are Euler's dynamical equations for a torque-free rigid body. And you're saying, well, wait a minute, that's not what I know. This is what I've seen those, right? Everybody's seen these. But I claim these are the same. And here's why. Omega 1, omega 2, and omega 3, here are x, y, and z. And there's a dt here. So if I divide dx by dt, I get the omega dots. Then the question is, what are all these A, B, B things? Well, Euler had a habit of not writing square. When he wanted to square something, he didn't write a squared, he wrote A times A. So this is really a squared, b squared, and c squared, and these are radii of gyration. So moments of inertia can always be expressed as the mass of the body times the radius of gyration squared. And since there are no torques on the right-hand side, you can divide through by mass and replace each of these moments of inertia by a square of a radius of gyration. So these are exactly the same equations that Euler that we today call Euler's equations. Now I'm going to talk a little bit. I'm going to do a stability analysis. If we spin this body, let's say about this axis, what can we learn about stability? So here are the same three equations we had before, and these L's are the principal axes of inertia of B, body B for the mass center BO. The angular velocity of B in reference frame N can always be expressed in terms of unit vectors parallel to the central principal axes of inertia. And these I's are the moments of inertia of the body about those L's, the lines. Now, so here we have Euler's dynamical equations, and we want to study an exact solution, namely a spin of constant rate about the three axes. So you can see this satisfies the equations identically. If you put the omega 1 and omega 2 equal to 0 in here, this drops out. There's an omega 1 dot, and 0 dot is 0. So that goes, this goes. Now S is a constant, and when you differentiate it, you get a 0. And here you get two zeros, so you even have twice as much zero-ness as you need to make that 0. So this really is an exact solution of those equations. Now we're going to add some perturbations. We're going to say, okay, we're going to let omega 1 equals 0 plus a perturbation epsilon 1. Omega 2 is 0 plus epsilon 2, and omega 3 is S plus epsilon 3. And we're going to substitute back in here and linearize in the perturbations. So we get that. Now the third equation isn't very interesting. We just get that the third perturbation just stays at its initial value. But there's more to do here. If we assume, well, first we can put this in matrix form, these two equations here in matrix form, and then assume a solution of the form e to the lambda t. You've all done that in math class. And you get a characteristic equation where you get the determinant of lambda times the 2 by 2 identity matrix minus this equals 0. Now that leads to a characteristic equation, and we can solve that for lambda by taking square roots. All right, now, we know we have an unstable solution when lambda is real, because one of the roots is positive, and the e to the lambda t just keeps getting bigger as t gets bigger. So what makes it real? It makes it real when the quantities in parentheses have the same sign. When does that occur? Well, when they're both positive or they're both negative. So if this is positive and this is positive, then I2 must be greater than I3, and I3 must be greater than I1. So I3 is in the middle. Or they're both negative, in which case I2 is less than I3, and I3 is less than I1. And again, I3 is in the middle. So when it's in an intermediate, the axis of intermediate inertia we're spinning about, we would expect the motion to be unstable. Now, if this is imaginary, it reduces to a sinusoidal state. And the way it's imaginary is if these two have opposite signs. Either this is negative and this one's positive, or this one's positive and this is negative. And you can go through the same sort of argument, and you find out that means that if I3 is either the largest of the three or the smallest of the three, we would expect stable motion. Now here's a book, and I can flip this book around these three different axes, and here's what I would expect to see. That the central principal axis of maximum moment of inertia is stable, the minimum is stable, but the intermediate one is unstable. So we would expect to see that, and it just so happens I have a book here, and I can show you. Here, this is the maximum axis, and if I spin it like that, I better not break my computer. You can see that it's very, yeah, maybe. You can see as I do that, it's very happy. Doesn't object, no matter how much of a perturbation I give it. And this is the minimum axis spin, and it likes that. But if I try the intermediate one, unless I do it perfectly, did you see it twist? See, try doing that someday. You can't not make it twist. See, so the math says this is what I should expect, and that's what really happens. Okay, so now we'll get back to the satellites. If we so now here we have this satellite coming off the booster, and it's a minimum axis spin, right? It's an axis of minimum moment inertia. It should be stable according to Euler's equations. But remember, it did that. So we have ourselves a problem. Why did it do that? Well, I decided, you've never seen a modern analysis for this, so I decided to do one. I wrote the equations of motion of a 14-body model of this. A 5-body model having 14 degrees of freedom. The degrees of freedom are this. A point in the rigid body, such as the mass center, has 3 degrees of freedom in space, translational degrees of freedom. The rigid body has 3 rotational degrees of freedom. And I included in my model the 4 antennas. But I modeled them as rigid bodies that have azimuth and elevation gimbals, because they're much easier to model than continua. So each one of these has 2 degrees of freedom and adds up to 14. So now what I'm going to do is show you an animation of this. See if I can find my right there. Yep, I'm all set here. All right, now remember, this thing's coming off the booster at 750 RPM, which I input. I had to estimate the mass of the antennas. I made each one of them 100th of the mass of the main body, which was only 30 pounds. And I took a guess on the damping constant. So I have a spring, a rotational spring, and a rotational dashpot resisting motion of these relative to the body. And I gave it a perturbation of 0.001 radians per second along one of the transverse axes, which is It's 1/78,540th of the spin rate. So this is, the perturbation is about 1/80,000th of the spin rate. And so here we watch what happens. Those little perturbations start to build up. Now you're going to see some aliasing. If you've seen a car going down the street where all of a sudden the wheels look like they were going the other direction, you'll see some of that. It has to do with the frame rate. But don't mind that. I mean, this thing isn't really stopping, and it looks a little funny, but it has to do with the frame rate versus how many frames per output lines of out. What the time step is on the simulation.
How much time did it take?
Oh, this took I don't know, a few minutes, five minutes or something. I don't have that at my fingertips, but it isn't very long. It's not like an orbit or something. So that's what they observed. So you can see that that's what happened. All right. So what's going on here? Wait till it should stop any second now. I can kill it. Now, if I, what happened to my, oh, there it is. If we look at the energy versus time, you can see that it starts off with quite a bit of energy with that high spin rate, and then the energy losses through the boom motion causes some damping, and then it starts to tumble and they don't move anymore very much. And there's angular momentum as a constant the whole time because there are no external torques. So you have this huge energy loss while nature is forcing the angular momentum to be conserved, and so it has to change what it's doing. Now, what I decided to do is to see what happens if you fatten up the spacecraft. So what I did here was I said, let's say that it's really stable. A maximum axis, and see what a stable motion looks like. And what I did, I made it fat like a hamburger, so I called it hamburger. And now it came off the booster at 750 RPM, and I gave it a transverse perturbation of half of that, 375. Not 1/80,000th, but 375, a huge perturbation, unlike the other one. And we'll see what energy dissipation does when we have a maximum axis spin. Now, this is just barely maximum. This is not something that's really maximum, it's just slightly maximum, just almost a sphere. So what you see from this is that whether or not we're doing a maximum or a minimum axis spin really matters when you have energy dissipation. When you don't have these booms, the energy dissipation, there's no energy dissipation, so both the minimum and the maximum axis spins are stable. When you have energy dissipation, the maximum axis stabilizes from this huge perturbation, whereas the minimum axis spin destabilizes from a tiny perturbation. So that is what happens there. Now, here's the energy and angular momentum again. So here again we have this huge decrease in energy, and again we have angular momentum conserved. But if you look at the nutation angle, the angle between a line fixed in space and the angle fixed in the spacecraft, the first one came off the booster with no perturbation at all, ended up at 90 degrees, flipped over. The fat one, I gave it a huge perturbation. It starts off with a 24-degree misalignment and ends up back at 0. So you can see that qualitatively they're quite different. Now, is there any other explanation for this? Can some other thing be responsible for besides this flexing of the antennas? Well, what about misaligned principal axis for the mass center? If the geometric symmetry axis and a principal axis for the mass center are not the same line, and you start this off spinning about the geometric axis, what will happen? Well, I did a simulation of that, and take a look at that. There we go. And let's see what the name of that one is. It's C1. Okay, now there's no energy dissipation at all. I've taken the damping out, but I'm starting this thing off spinning about a 1 degree misalignment. So in other words, I started off spinning about the geometric symmetry axis, but the principal axis is misaligned 1 degree. So you can see it has the same sort of behavior, but there is a difference. And you can see the difference if we look at the nose trace. And so here's the nose trace of the Explorer I. It starts off, if you're looking at the nose, it starts off here, and as time goes by, it kind of spirals out. This is a unit vector, so eventually it spirals out so that the vector is perpendicular. It's parallel to the screen. It's perpendicular to where it was, and you can see this is a unit square here. So it spirals out slowly as that takes place. Now, the one I just showed with the misaligned principal axis does that. There's no spiraling. It's a mess already from the get-go. You see, so it has a different qualitative behavior. So the question is, which one was it? Well, if you look at the way they calculated how this, what the attitude was, when the nose of the vehicle was pointing at the ground station or the tail, they got a null. The data stopped coming in. So for a short period of time, you can think of the orbit path as a straight line. And from high school trigonometry, this distance from here to here is d over 2, and that's r. And so the tangent is rise over the run, and the rise is r, and the run is d over 2. And r divided by d over 2 is that. And they concluded that if a precessing satellite passes a receiving station at a distance r and has an antenna with nulls off the nose and tail, it can be estimated from close examination of the signal strength record when the nose of the satellite is pointing at the station on the approach and when the tail is pointing at the station after passing. The distance d and the distance r then can be used to give a rough estimate of theta. And so they figured out that during the second orbital pass of Explorer I, a very slow periodic fluctuation in signal strength became noticeable, in addition to the flutter caused by the 750 RPM rotation rate. By the end of the first orbit, it was already evident that the 750 RPM axial rotation rate was being damped out. A slow precession soon transferred the rotation to an end-over-end, the rotation axis to an end-over-end tumble with a 9 RPM rate. So in those, they were able to figure out that it was the antennas and not the misaligned axis. So to summarize, we have a case where you have a hamburger-shaped satellite. Since all spacecraft energy dissipation, if you have a hamburger-shaped satellite, you're going to get a stable motion. But if you have a hot dog-shaped satellite, you don't. It's going to be unstable. But that presents a problem that a nose fairing of a rocket is more amenable to housing a hot dog than a hamburger. Now, I know we're getting close, but if you give me another few minutes, I'd like to show you how this is resolved. Does anybody want to see that? Okay, good. Okay. Now, it was a dual spin satellite concept came up with by the Hughes Aircraft Corporation. They said, well, what happens if we put a rotor on the hot dog-shaped satellite and spin it in the direction of the rotation of the satellite relative to space? Now, why in the same direction? Well, remember, angular momentum is conserved. So if the disk is rotating relative to the satellite in the same direction and angular momentum is conserved, the satellite has to rotate slower in the other direction to compensate for it, to conserve angular momentum. So I'm going to show you an animation of this, and we'll pull up my trusty animation. Now, the very first thing I'm going to do to show you that this is no gimmick, I'm going to do a run where the rotor is welded to the spacecraft. So we still have an unstable minimum axis spin. So let's just do that one first. The disk is part of the spacecraft. It's not rotating relative. And it's back to the case with the energy dissipation, the beams, and so you can see that we're back to the case we had before. So by putting the rotor on there, I'm just showing you I didn't make it into a maximum axis spin. That's not really stopping. So it's wearing a tutu and it's still doing the same thing. Okay, so you see that without the rotor spinning, we still have the same problem. But, let's see, I want to kill that. If now I'm going to rotate the wheel in the same direction as the spacecraft as it comes off the booster. And I've calculated what it would take to slow down the spacecraft so it's not rotating at all in space. There. So you can see with a little fine-tuning control system on there, you could get rid of the tumbling altogether. So that was Hughes's solution, was to put rotors in spacecraft that were shaped like hot dogs and then put the hot dogs in the rocket nose fairing and everything was happy. Now that's all I had to say, and I'd be happy to answer any questions. We have the lights back. Yes.
Was that last simulation you showed was zero torque between the hot dog and the hamburger?
No, there's a motor in there that spins the wheel up relative to the.
But no active. Once the spin gets going, then it's.
Yeah, once it's up to speed, the torque would just go.
It's faster.
Yeah, I just put in I had to get it started, so I spun it up from nothing and then kind of. No, I just. That's why it's probably wobbling. No feedback. I just spun it, Yeah.
It's an oversimple question, but why is spacecraft spinning at such high rates on their axes to begin with?
Well, that one they thought it would make sure it was nice and stable, and they were wrong. But there are a lot of reasons it's used for stability. I mean, you really do want to. I mean, now you can. Now we have things that can unfold, and you can make a hamburger out of them and spin them for stability. Not 750 RPM, but there's a lot of, in rotors, we have lots of satellites with spinning rotors in them that all kinds of different ways. There's, they usually are 4 of them, and they're on the legs of a pyramid. And they have something called a pseudo-inverse, where you take the 3 torque components you want, you distribute them among the rates that these 4 wheels have. And there's a whole theory of that. You can get into that in your spacecraft course here. They do that. You have courses in. Yes.
In fact, Professor Turner's book about vector dynamics, he teaches that in undergraduate course. The example of linearizing the Euler equation is there, and the conclusion that you can go either maximum or minimum. That he teaches that in 134, I believe.
Well, that's good.
But this is linearized analysis. And if you want finite amplitude, you have to solve the nonlinear equation.
Right, which this was. The animation was the nonlinear.
But you don't need to do that to conclude that if you introduce the sedation, you can also come to this conclusion without solving the equations. So just insisting that the rate of change of the kinetic rotational energy decreasing, then you exclude the minimum axis. That's well known, without solving the equation.
Let me explain what he's talking about. There's what you might call a heuristic argument for why, without the booms, the maximum and minimum axes are stable, intermediate one is unstable. And it has to do with the fact, as I showed on those plots, you have this angular momentum that's conserved. It's a constant. And the energy has to go down. Now, if you look at the formulas for the magnitude of the angular momentum vector and for the total kinetic energy, they have the same symbols in them. Each one has 3 omegas and 3 i's. And so they're these functions of the same variables. Well, if you know that one of those functions is a constant, and you know that the value of the other one has to be going down, and something has to give, and there's sort of a heuristic argument you can make that says, well, therefore the spacecraft has to switch axes about which it is spinning in order to accomplish that. In other words, nature makes it do that. I think that's what you were trying to say, right? So can they take this course that you're describing?
Professor Carlo teaching me.
Right this minute?
134.
Is it offered next term?
Where is Professor Carlo?
Okay, you should sign up for it.
Okay, I think we're kind of out of time here, so let's just
Thank you very much. Okay, now, can I didn't go over too much. I asked them and they all said yes.